So we've defined what the divergence theorem is. Now, and we've gone through where it comes from, or a derivation of it. Now let's look at some applications. So the first application, well, this application will be on the continuity equation in fluid flow. And this is described on, you should see page 797 through 799, the continuity equation for fluid flow. So in this context, V, which can vary in space, x, y, z, as well as time, is the velocity field of a fluid. And again, we have our we have a stationary control volume. And it has volume V, and it has a closed surface S. So it's an imaginary volume in space through which the velocity field can flow without interacting with this volume. It's just a perfectly permeable sort of imaginary volume. And let's say that sigma is a scalar quantity that can vary with, in general, with x, y, z, and time. And this corresponds to the mass density of the fluid. And the units are in, for example, kilograms per meter cubed. It's the amount of mass per volume of fluid. So the total mass of the fluid in the volume V is, we'll call that capital M, and that's equal to the integral over V of the mass density throughout the volume. So we're integrating the mass density throughout the volume, and that gives the total mass contained within the volume. And the rate change of mass with time is equal to the rate change of that integral But remember, we have a fixed volume. It's fixed in space and in size. So there's no change in the volume part of this integral. The only change is that could be happening is with density. So the rate change of the mass of the volume is related to the rate change in the density in the volume. Let me move this up so I can have a little more space here. So the continuity of the fluid requires the following. It requires that the rate increase in mass, m, is equal to the rate of net mass flowing into the volume, V, right? So if there's a net rate of mass flowing into the V, then that contributes to an increase in mass, plus the rate that mass is being created. again in our arbitrary control volume. And mathematically, we can write that as dm dt, which, as we showed, was equal to the integral over the volume of d sigma dt, the rate change in density, and that's equal to minus the flux of mass out of the volume by fluid flow. So the positive of this integral is the net mass flux out of the volume. The rate of net mass flowing into it is equal to negative this integral. And then plus, we might have, in general, it's possible, we could have a net source of mass, which we'll call F. It's some rate change in the mass supplied by this source of mass. And so this is the rate of mass created integrated over the volume. So this is a statement of continuity. So this continuity equation is also a statement of the conservation of mass. Right? It states that any mass change within the volume is related to any mass leaving the volume plus any mass created within the volume. So this is a equation that we have to solve. This is one equation that has to be met when we describe or when we model or simulate fluid flow with mathematical equations. So this is a required law for fluid flow. But it's somewhat of it's a difficult equation to use because it's an integral equation. And so it's the objective here is to get rid of the integrals. Now, how do we do that? Well, you can imagine that if every integral was an integral over a volume, then we could express the whole equation as a single volume integral. But the problem is that we have this mass flux equation as an integral over the surface. But the divergence theorem allows us to convert this surface integral into a volume integral. Right? You'll recall that the integral over the surface of the flux of whatever is moving, here this is a mass flux because it's moving with the velocity field of the fluid. This is equal to the integral of sigma times the divergence of V integrated over the volume. And I need to write this. I want the divergence of sigma times V here, integrated over the volume. And so if we were to make this substitution, then we could write everything under a volume integral. We could write the full equation. So that's the rate change in density And I should have written that as a partial derivative, because we're keeping the location fixed. So the location we're looking at the rate change in time with the location fixed. So we have a partial derivative of sigma with respect to t plus divergence of sigma times v, which is the second term here, minus f, which can vary in 3D space as well as time, which is our source term, times dv. And that's equal to 0. So I basically brought these two terms on the left-hand side and written the whole equation as a volume integral. Now, one thing I'd like to point out is that since v is arbitrary, that is, no matter what its shape is, this integral always turns out to be 0, then that must be, because it's arbitrary, it could be a square, it could be a circle, it could be anything, that must mean every point within that arbitrary volume, the integrand must equal 0. That is the partial of sigma with respect to t plus divergence of sigma times v minus f must equal 0 everywhere within that volume. For example, if there was one and this is also assuming the integrand is continuous. We can imagine looking at a very small point in which this integrand was not equal to 0. And if it's continuous, then the adjacent points must also not equal to 0. And if we define the adjacent points as our arbitrary volume, then the fact that they're not equal to 0 violates this equation. So that must mean that every single point within this arbitrary volume, the integrand here must equal 0. So we now have a new continuity equation of d sigma, partial sigma with respect to t, d sigma dt, plus the divergence of sigma times v is equal to our mass source. And in most cases, i.e. not quantum mechanics, most cases that we would apply this in to earth science, for example, that's not quantum mechanics, F is equal to 0. There's no source of mass. So the fluid continuity equation that we can use is a partial differential equation. We've eliminated our integral equation, and we're left with a partial differential equation in terms of density and velocity. And if we were to write this out, we would have the partial derivative with respect to x of sigma times Vx plus the partial with respect to y of sigma times Vy plus the partial derivative with respect to z of sigma times Vz is equal to 0. So that's writing out all of the terms in the full form. There's a special case that's often encountered in some cases, and that occurs when sigma, the density, is equal to constant. So this is described as incompressible flow. And in that case, so we have the partial with, so d sigma dt is equal to 0. And if we carry out the del operation on sigma times v, we would get the gradient of sigma dotted with v plus sigma times the divergence of v is equal to 0. And if sigma is 0, then the gradient of sigma is equal to 0. And so we're left with the final continuity equation of the divergence of v is equal to 0 for incompressible flow. And that is to state at every single point in the fluid, there's no net flux of material out of that point. In other words, the rate change in the volume of the fluid is constant at every single point in the fluid. So that was one application of the divergence theorem. Again, the divergence theorem allowed us to go from this integral equation, eliminating the surface integral, okay, to change this into a volume integral, and then because everything's as a volume integral, then we can take at each point the integrand being true, and that gave us a partial differential equation, which we could solve using partial differential equation methods.